Well, thanks for coming back. We will pick up where we left off last time, which was talking about these monoids of the mapping class group, which had some consequences for contact geometry. So let me just remind you what those were. So we had, first of all, those which correspond to Stein fillable structures, those which correspond to tight contact structures, and those ones which could be factorized into positive den twists, and we were just teasing out the differences between these. And I had started talking a little bit about Stein cobordisms, so we should probably draw a picture of such a thing. I mean, just a sort of schematic, which I didn't do yesterday. So we start from some manifold M with a contact structure C, and that'll be what's known as the concave boundary of our cobordism. So these are, again, directed cobordisms. They only go in one way, having a cobordism from MC to M prime C prime certainly does not guarantee one in the other direction. And the theorem I had written up last time, due to Eliashberg, was that this cobordism will be Stein if and only if it is just M thickened with certain handles attached, so arbitrary one handles, and then these two handles with the special framing. So two handles along Legendrians with framing TB minus 1, where the TB is the Thurston-Benniken framing, which is just given by the contact structure as you go along the Legendrian. So what we can do is look a little bit at how these handle attachments affect, or what they correspond to in the level of both the three-manifold and the structure of the open book decomposition, which is fairly straightforward, but should be at least said. So for the one handles, what are these? This is just D1 cross D3. And in the three-manifold, let's see, in M, what are we doing? Well, we're taking a neighborhood of the attaching sphere here, so an S0 cross D3, with the boundary in the other direction. So this is D1 cross S2. So we're just taking a connect sum with an S1 cross S2. So M prime is M connect sum S1 cross S2. And if you go back to this first open book decomposition example I gave you yesterday, you can work out that for an open book decomposition, this is just adding a one-handle, a two-dimensional one-handle to a page and extending the monodromy by the identity over it. So you're not really doing much. This is just adding a one-handle to the page. Okay, and not doing anything to the monodromy. So this is sort of not the interesting, or not a particularly interesting thing. And I guess as is standard in, well, as is done quite often in the study of four manifolds, one doesn't really care about one handles all that much and goes on to consider the two handles and cobordisms built up from two handles. So for two handles, of course, things are a bit more symmetric. We have a D2 cross D2, and then in the three manifold, we're just replacing the boundary of this one cross this one, so an S1 cross the D2 with, symmetrically, this one cross the boundary of this one, a D2 cross S1, with this framing gotten by this integer here, the Thurston-Benneken number -1. So this is just a TB -1 surgery, a den surgery with coefficient TB -1. And then we want to see what that looks like in the open book decomposition. So we need to know a little bit about how Legendrians interact with open book decomposition. So let me just give you a fact. Which I'll attribute to Giroux. There's a bunch of different ways of seeing this, but his is the easiest. That if L is a Legendrian, not necessarily connected, if and only if it can be realized as on the page of an open book decomposition. So L can be realized, let's just say sits. We can, let me say this, is a Legendrian where? In a contact manifold in C, if and only if it can be realized L sits on a page in a supporting open book decomposition. And recall the way this Thurston-Winkelkemper construction went. The supporting open book decomposition for a contact structure, the contact planes are close to the tangent space of the plane, so the page framing and the Thurston-Benneken framing will be the same thing. So Thurston-Benneken number of L is just the page framing. Another fact we need, or a construction, which is due to Licorice, I guess, and the proof of this fact I mentioned yesterday, that the mapping class group is generated by den twists, is how to connect up den twists with surgery. So den twist, this fact 2, the den twist how L corresponds to a surgery -1, which has a framing -1 with respect to the page framing, so -1, so TB minus L. TB -1 surgery. And how do we see that? Well, it's actually very simple. If you haven't seen this before, it's probably worth considering. So we look at a little bit of our link L, or our not whatever L might be, our one manifold L, which is sitting on a page. So let's draw a little bit of the page around it. So there's my page sigma, so L continues off, does something, comes back. And let's look at some of the pages around here. And let's consider a little neighborhood of L, which goes, so not a neighborhood around L, but a little solid torus on which L sits. So I'm just cutting out this solid torus here. L sitting on top of it. And I note that if I do a den twist around L, well, what's happening to this rectangle I've drawn here, which is a meridian of a solid torus? Well, it ends up just going up over something like that. So we see exactly that we're doing a surgery, right? We're cutting out these meridional disks and we're gluing them back in with this additional longitude attached to them. So that's exactly TB -1 surgery, which is what we wanted. So we can put all of this together. And arrive at the following theorem. Which is that if there exists a Stein cobordism X from MC to M prime C prime, well then I can find well, making an if and only if there exists an open book decomposition sigma D for C, and some word in positive then twists, which I'll call psi. This is in my monoid then plus such that if I take my open book decomposition with the same page and the composition of these two monodromies, that should support M prime C prime. So I'll leave that theorem as an exercise from the things that had already been said. So what does this tell us in terms of our monoids? Well, it tells us, well, corollary restatement if you want, that then plus is contained in Stein. Okay, so if you have a positive factorization of a monodromy, you have a Stein filling of the thing, just by taking MC to be the empty set. On the other hand, what you don't have, though, so is the other way. Okay, so you have things which are Stein fillable. You have certain open book decompositions of Stein fillable context structures which are not factorizable in terms of then twist. So if you find the positive factorization, that's great. If you can't, then that's not so great. So this symbol there is a theorem due to myself, and then by slightly different ways due to this team, Baker, Ettner, Dan, Horn, Morris. And since I wrote their names out yesterday, I won't write it out again. Right. So that's, in some sense, the state of the art when it comes to understanding rigidity through open book decompositions. I should mention, I guess, a sort of amusing corollary to this. Observation theorem due to Ettner and Honda. Which is that for any contact manifold, there exists a Stein cobordism from C to a Stein fillable manifold. Okay. So for over-twisted, tight, whatever, it doesn't matter. You can find a Stein cobordism to a Stein fillable manifold. And again, that's a reasonably easy exercise from what I've written up there. Okay, good. So that's rigidity. Let's move over to flexibility, trying to detect it through open book decompositions. Yeah.
In terms of like elements in mapping clusters? So
Well, if they're positively factorized, then yes, I mean that's exactly what you're building up with these handles, is a Lefschetz vibration. I mean that's that.
Right. It's a PEL. Okay, yes, okay.
Yeah, it's a PEL. In the old language, I guess. Okay, so where was I? So we want a theorem sort of corresponding to this theorem, but for over-twistedness, and we have one. And we will attribute it to Eliashberg and Giroux, our favorite names. I'm not sure that either of these ever wrote anything like this. It follows directly out of the two theorems of theirs that I've written up to this point, which is that the following two things are equivalent, that C is over-twisted. Well, MC, I'm going to give myself more room. MC over-twisted if and only if there exists a supporting open book decomposition which is negatively stabilized Okay, i.e. it has one of these H minus sum ends that I drew up here yesterday. And let's see why that's true. Kind of a proof. Well, for one direction, let's go back this way. That's the easier one. Well, first you need to know something I'll leave as an exercise. Why not? H minus the Hopf link, i.e. the one whose page is an annulus and whose monodromy is a negative den twist, supports an over-twisted structure. We saw yesterday that it was S3 topologically. In fact, you can see actually fairly clearly, you can identify an over-twisted disk in there. And as we saw, when we're doing this Murasugi sum, we're really just taking connect sums of the manifold. So the over-twisted disk in H minus comes along for the ride into MC. And we find that M itself, MC itself. So MC also has an over-twisted disk. So that's nice and easy. For the other direction, we need to know a little bit about homotopy classes of plane fields. This was all done by Pontryagin, maybe, and Hopf, and people like that, long, long ago. And then you can find a nice write-up of this in a paper by Giroux and Goodman, if you're interested. It's a unique paper that they wrote together, where it's shown that homotopy classes various invariants are given for homotopy classes. Plane fields have an invariant, a couple of invariants. The one we're interested in is what's called usually the three-dimensional invariant D3, which then admits Z action, very, very roughly here. Z action, and which such that the this negative stabilization shifts by 1. Okay, so what do I mean by this? And what's the point to all this? Well, if you're over-twisted, right, we're starting with something which is over-twisted. We saw yesterday that Eliashberg reduces the study of these things to the study of homotopy classes of plane fields, over-twisted structures. There's a unique over-twisted structure in each homotopy class of plane fields. So what we get out of this algebraic topology here is that we can find a homotopy class of plane structures such that when you negatively stabilize an open book in it, you get to the homotopy class of of the one you started with. Okay, if that makes sense. You start with one, you reduce to its homotopy class, you go to another homotopy class, which is then shifted up there by this negative stabilization. But then, since both of these are going to be over-twisted and they're in the same homotopy class, they have to be the same contact structure, right, by Eliashberg's theorem. So let me write that in some way, which is hopefully a little bit better. So there exists contact structure we'll call it C prime, such that I'm going to write it like this: D3 C prime C equals 1, i.e. the difference in their D3 invariant. So if I take any open book decomposition for C prime, I negatively stabilize it, well, the result, again, as I said, is over-twisted and is in the same homotopy class of the one I started with, C. So I get an open book decomposition for C. which is what I wanted, a negatively stabilized open book decomposition. So, maybe slightly complicated, but sort of indicates how these theorems interact with each other. I think it's worth seeing. So it's a nice condition, but again, you know, there exists a supporting open book decomposition. It doesn't tell us by any means that every supporting open book decomposition will be negatively stabilized. So if we're trying to detect over-twistedness from a given open book decomposition, we need something stronger than this. And some string of results which strengthen this. And I might as well write down some names. So first, Noah Goodman, a Gomp student, and his thesis came up with this notion of a sobering arc, which I won't define, but again, it's a sufficient condition to determine over-twistedness, which is a bit weaker than having this negatively stabilized thing, so it's better as a detector. Around the same time, a very similar criteria was developed by Honda Kazaz-Madic, which is the more well-known theory or framework of right veering. So right veering determines yet another monoid in the mapping class group, and let me just define it since it's a fairly ubiquitous term. We say that a mapping class B, what should we say, maps, well, let's just say it like this, is right veering if for every properly embedded arc call it gamma in my surface and isotopy phi such that gamma intersects phi of gamma minimally, i.e. there are no bigons. Phi of gamma is to the right of gamma near the boundary of the surface. So it's a mouthful, but it's the definition. And so possibly better described just through a picture. So if we let this thick line here be the boundary of our surface, and we look at gamma sort of near to that surface, which is our properly embedded arc, what we demand is that phi map it off in this direction. And moreover, that it not just come back and bound a bigone or something like that. That's why we want intersections to be minimal. So it maps to the right in some essential way. So right veering, I think, first came out of the work of Thurston when he was working with braids. This was the first application of it to contact geometry, and it stuck around because it gives a great criteria for telling when things are over-twisted. Again, it's not a complete criteria. So if you don't have, if you have something which is right veering, that doesn't necessarily tell you anything. It might still be over-twisted. So then the state of the art, I guess, on this is work of mine, which is called consistency of monodromy, which I won't define entirely. Well, I won't define it all because it's very complicated, much more complicated than this. But it's a method. It assigns to. It's a way of checking tightness from an arbitrary open book decomposition. Let me just say that. So the theorem involved here is that the following are equivalent. One, a given context structure is twisted. Two, some supporting open book decomposition is consistent. And finally, each supporting open book decomposition is consistent. So it's a very complicated algorithm for, from an arbitrary open book decomposition, detecting over-twistedness or tightness. Sorry. Tight. So it exactly identifies this monoid of tight contact structures. Okay, so that's really all I wanted to say about that. We're doing fairly well for time. And now I want to move over to less topological methods and talk about Heegard floor homology and its relation with all of these notions. So let's say Heegard floor homology, with the hat on it, open book decompositions, and contact structures. Okay, so how do we want to set this up? Let's see what I have. So let's start. I should say that the treatment I'm giving it here is mostly due to Honda, Kazas, and Maric. So what do? We want to, what does Heegard floor homology do? Well, we've seen it described fantastically by Adam. For us, I'm going to think of it as something which associates to a contact manifold. Well, sorry, if you wrote that down, let me say it differently. It associates to a contact manifold this gadget, the Heegard floor, the hat version of Heegard floor of M in the spin C structure corresponding to that contact structure. And I won't say anything more about that, but sitting in this algebraic structure here is something called the contact element, C hat of C, which is just a class, and it has the following nice properties, which I'll write as a fact, which is that if C is over-twisted, then this class vanishes, and if C is Stein-fillable, it does not. It does not. Okay, so none of these implications go the other way, but what it can tell you is that you are not in one of the extremes, basically. So it does give you a criterion for tightness, but it's not a complete one, but it's still incredibly useful. And what we'd like to do is try and get some more information out of this, sort of refine it so that it doesn't just see the extreme, it sees where you are in between the extremes. That's what I'd like to do. So to do that, I should probably start by showing you how to define the Heegard floor complex in terms of an open book decomposition.
Andy,
Yeah.
want to reserve your additional time?
I don't know. I mean, yes, I should, but I won't, just because things start to get complicated. So you can mentally insert a negative sign in there. But, yeah, or I can just define my invariant to be sitting in the other one, which I'll do. So I hope that's not confusing, but an exercise is to work out what the where the minus sign should go in all this. Okay, so open book decomposition. So what we want to do is start out with our usual data of an open book decomposition. So, and then we'll take some additional information. So gamma, this will be a collection of disjoint properly embedded arcs. Okay, and as I had indicated yesterday, one can cook up from this sort of a specialization. I mean, you cook up an open book decomposition, but the open book decomposition then is sort of a specialization of Heegard decomposition. So we can expect it to have the whole Heegard floor complex sitting in it. In fact, it does in a very nice way. I want to add one extra constraint before I draw a picture, let's isotope P such that P is gamma. Again, this criteria I had earlier is to the right. P gamma I is to the right. Gamma I near the boundary. Now, this doesn't mean that it's right veering, because you might have bigons, right? So I don't care about minimality of intersections anymore. And so let me, in this setup, give an example. Let me give our old friend H minus with gamma, just the arc that I drew yesterday. So what was H minus? It was this annulus, which we then thickened up. We considered an arc sitting in it, and then we finished up the rest of the drawing like this. And so we had our arc. A little bit better. And if you remember correctly, so what did we do? We take our annulus, we thicken it up, we identify all these lines on the boundary, we compress those, we glue the top to the bottom, we glue it by this negative den twist around here. So yesterday we had drawn the negative den twist as sort of going out like this. Today, since we have this going to the right business, what we want to is start out going to the right, and then it can come back. Do all that, and then go like that. So this is the picture we want with our conventions today. And as I had mentioned yesterday, one can see this as a Heegard decomposition, right? A manifold without too much difficulty. We have the handle bodies are sitting right there staring at you. Here's the one on the bottom, down here. And so what Adam has been calling an alpha curve, we can see as the boundary of my arc gamma cross, let's say 0, 1/2. And a beta curve then is, do I have my colors mixed up? Blue is for alpha, red is for beta. Is this guy. Right, and so since we're gluing this up to this, so then the alpha and the betas are the same. They're everywhere except for on this top half of the Heegard diagram. So we can see this bottom arc here showing up here. So the entire complex is sitting in half of the Heegard diagram. That's the specialization here, if you'd like. So, our complex now, we'll call it the pat with a little gamma under it, because gamma is a little bit different here than what it was in Adam's setup. Well, that's the same thing it was for him. It's these tuples, xi, xn, with the requirement, just to make this self-contained, I'll write it all using Adam's notation, so there should exist some sigma in the symmetric group in letters, such that xi is an intersection of gamma I with p of gamma sigma I. But additionally, since really we're thinking of, there's an intersection point, there's an intersection point. This guy on the end there, though, is the same as this one over here, right? Because it's really, apart from that, everything agrees. Does that make sense? So, say where hi, we are identifying boundary of gamma I to a point. So the complex we get over here is exactly the one that Adam drew this morning, right? We have 3 generators, we have one here, and then this one at the boundary is just a single guy. And our differential will do the same thing it always does, but we're going to write it a little bit differently to emphasize the structure of this thing. So instead of pi 2, I'm going to define pi 2 0. So it's going to encode in it this missing the base point thing. So for generators xy, pi 2, 0 of xy, we're going to say that D in this, a domain D is in pi 2, 0 of xy if, only if. So what should we have? We should have that the boundary of D sits in the gamma union phi of gamma. So in particular, it stays on the top of the open book decomposition, right? It doesn't go down to the bottom. And then the other thing we want is just as in what Adam had, that if we take the boundary of the boundary D restricted to my gammas as opposed to my phi of gammas, then I get y minus x as an oriented thing. So in my complex up here, I'm just being a little bit hand-wavy here, but I want to go quickly just to match it up with what was said this morning. We have, two generators here in the middle, then we have one at the end, and we have two domains, which are just these bigons. You can check. So your complex here is exactly what was drawn this morning. And I'll write it as a fact. If you've chosen your gamma such that it cuts D into not D, sigma into a disk, so if sigma cut out gamma is a disk, what I've done recovers HF hat of M with this spin C structure that I had mentioned earlier. And moreover, the contact class here is just the class of this point on the boundary. That's really the main point here. So this fact is a theorem due to Honda, Cousins, and Maric. So everything I did here is basically in their paper. So up in this picture we have here, we see that this generator is exactly the contact class, the point in the boundary. And so we can explicitly see it as a boundary and see it vanishing in this example. And if you think about it, that actually proves this first statement up here if we use this theorem here. Right? If you're over twisted, then you have a supporting open book decomposition which is negatively stabilized. So I can find such a summand, and then I can take the generator, which is one of these interior points, and then everywhere else is on the boundary, and then these disks here will send it to the contact class. Will vanish. We could also use this setup along with some of the Oswath and Szabo stuff to see that if C is Stein, then the contact class does not vanish. And how do we do that? Well, we start not from H minus, but from H plus. So I'm sorry, I'm a little bit disorganized here. So let's also draw the picture for H plus, just to emphasize the difference. Now, you don't really have to draw the rest of the open book decomposition since everything is happening on a page. That's the advantage to doing it this way. So we have our gamma, and now phi of gamma doesn't intersect it anywhere except on the boundary. So we have a single generator in our complex. Contact the class does not vanish. So that's great. I think I told you yesterday that this is the open book decomposition, which gives us the standard Stein fillable contact structure on S3. And so any Stein fillable thing can be built up from this by this Legendrian handle attachment I had mentioned earlier, and it's a theorem of Oswath and Szabo that there is a map going in the opposite direction from on this contact class. In particular, if it's non-zero on the bottom, it's non-zero on the top. So very, very hand-wavy, but we can verify both of these things.
Sorry, so
Yeah.
there's an element of H plus.
Yeah.
the image of a generator, and that's you know. So is that this is just the image of this.
Yes, but I mean, there are a few things that aren't really known. Right? We don't have. We'd like examples where one of them vanishes and the other doesn't, things like that. But yes. Was there a question?
Yeah. Oh, no. Sorry. Okay.
Okay. No, it's fine. Okay. So what am I saying? Great. Okay. So that's our setup. That's how you do Heegard flow. And so what I want to get back to after that little diversion is this idea of using all this machinery to sort of refine the information of the contact class. So now we're on to stuff that's quite a bit newer. And let me give you a theorem in this direction. So this is due to Van March, Van Morris, and myself, which is that there exists an invariant of a contact structure, which these days we're calling O of the contact structure, the O standing for a spectral order, which will hopefully make sense as I go along. This invariant, well, it's a natural number, it might be 0, it might be infinite, and it satisfies the following laundry list of desired properties. Well, first of all, it satisfies the same things that the contact element did. If C is over twisted, then the order is 0. If C is Stein, then the order is infinity. And then for stuff in the middle, well, it is non-decreasing under Legendrian or Stein-cobordism. And finally, perhaps most interestingly, it is something that we can calculate. So it's calculable from an arbitrary open book decomposition. Okay, not only is it calculable, it realizes all values, right? It's not just 0 or infinity. So we can give you examples of anything. So in some sense, it's extracting geometric information in the case when the contact invariant vanishes. It's still doing something, and it's using the Heegard-Floor complex to do that. So in 15 minutes, can I tell you about this invariant? Well, let's see. First of all, I should, let's see. So in what Adam's been talking about, we had this formulation of Heegard-Floor homology due to O'Clock-Zabo, the original setup when we were looking at maps of a disk into the symmetric, we'll call it the infold symmetric product of the Heegard surface, and then looking at the projection of those down onto the Heegard surface. So this was recast sometimes later by Lipschitz, what's known as the cylindrical reformulation of this stuff. And in this setup, what we're doing is we're looking at maps not of disks, but of, so this C will be a surface with boundary into S cross D2, and then again in the same way, projecting down. So the point being that such maps correspond to maps of this type. The idea being that we want C to be an infold branched cover of D2, so we can consider the map over here We can recover it over here by taking a point in D2, pulling it back to n points in C, and then we have n copies into S, which gives us a well-defined map in the n-fold symmetric product of S. Just for a very brief reason of why these two things should be morally the same. So what have you done here? So you've taken your high-dimensional symmetric product here, and you've replaced it with something much easier to understand, 4-manifold. Of course, you get nothing for free, so now, instead of looking at maps of disks, you're looking at pseudo-holomorphic maps of more complex surfaces, and it's exactly this complexity that we want to use to refine the information from the contact invariant. Very rough outline. So the idea is to use an old idea of Michael Hutchings in the context of embedded contact homology, or really in any version of contact homology that you like. And so his idea was, this is the reason that we'd like to do it like this. Contact homology is very similar to this setup up here. And so what we do with this cylindrical reformulation is to such a curve C, which is being counted by the differential, you want to associate some integer, which I'll call J plus of C. And this will just be given by, we can write it down. So it's as I said, it's supposed to record the topological complexity of C. So it's minus the Euler characteristic of C plus some terms, so n, where n is just the number of properly embedded arcs you started out with, as everywhere else, plus x minus y. So what are x and y? Well, C, remember, a pseudo-holomorphic curve should be corresponding to some domain between generators x and y in S. So that's what x and y are. And this notation we're using here is just that is the number of cycles in the permutation which we used to define these generators. So this, if we look at the domain corresponding to C, we can use some of Lipschitz's work to write this down just in a combinatorial formula that we can read off the page. So this is 2 times in x. So again, this is just using the same notation Adam had, plus in y of d. So the point measures, which I won't even bother to define because I don't want to run out of time, but the point is it's something we can read directly from the open book decomposition, from the domains on the page. There's a nice combinatorial formula. So what do we want to do with this J? Well, we want to show that it has a couple of nice properties. First of all, it's non-negative. Secondly, it's additive under pasting together of these curves C. And what that gives us is that it allows you to decompose the differential in Heegard-Flor, so the D, call it H hat. So it's 0, 1 plus boundary 1, 72 plus that, where this boundary I is now counting curves whose J plus is 2I. So J plus is always even, among other things. So we decompose the differential, and then this additivity business tells us that if you look at how should we say it? Let's just say that the sum, well, for all integers k, sum over all numbers such that I plus j equals k bounded I bounded j should be 0. So d0 squared is 0, so we get a homology theory there at the sort of the lowest order. But when we start to add in these additional terms, things get more complicated. And so we would like to organize all of this into a spectral sequence, which I won't try and define here, but I'll say what's going on. So we have a filtration on a differential. We don't have a filtration on the complex itself, so we need to do a little bit of additional algebraic mumbo jumbo here. We want to create a new complex, which I'll just call CF, which is curly, and this will just be Z's worth of the original complex, CF hat. And then on this complex, we define a differential. So now the differential, I don't know, what should we call it? Differential, whatever, of x is now just like, I guess I never actually wrote down a differential for the Heegard floor complex. It doesn't matter. Adam had written it down. So it's, well, say it like this. xi, where I is the guy in z, this is just the sum over y, and the sum over domains d in pi to 0 x y, which satisfy this Euler, Maslov index thing that Adam had written up. And we want, so that again, I'll just use the exact same notation that we had earlier today. We have this moduli space, which is 0-dimensional. We can count it, and it will give us the coefficient. And now we need to decide at what level this should be, and it will be at I minus j plus b over 2. So feel free to write down the formula if you want. I don't know how much you'll get out of it. The point being that having done this, we now have a filtered complex. If you have a filtered complex, you can define what's known as a spectral sequence. And I will just call this the Heegard floor spectral sequence, which is just, well, I don't really have any time left. Well, if you know what a spectral sequence is, great. And I'll make a definition, and I'll say that the order of, so what all data have we used here? So we started sort of implicitly with an open book decomposition and a collection of arcs. And there should be an almost complex structure in there, but I'll suppress that for now. So this is the minimum k greater than or equal to 0, such that the contact element in this thing, let's say at the 0 level, it doesn't matter because they're all the same, vanishes at the k plus first page of the spectral sequence. So what does this mean? Well, it means, among other things, that if the contact class is killed in the homology corresponding just to d0, remember I said that if you square this, you get 0, that is equivalent to the order being 0. If you need more complicated things to kill it, then you have to go further into the spectral sequence, and this is just measuring at what point all of this happens. And our theorem is that we can detect the sort of the minimum over all open book decompositions from a given open book decomposition. So my second definition here, let's say that OC is the minimum of this thing I wrote up there, sigma gamma over all choices of data. Okay, so it's an invariant of the contact structure, and we can calculate it from an arbitrary open book decomposition. Well, I don't really have much time left, so what sorts of things can I tell you about this? I can't tell you much more about its structure. I can say, what it's good for, I suppose. So, well, before that, let me just say briefly, we do have examples. So let's say for every, what should it be, m greater than k greater than 0, we can give you a family indexed by these, a family of context structures C in K, such that the spectral order of these things lies between K is greater than or equal to K minus 5 and less than or equal to K. So we can make it as big as we want or as small as we want. I'm quite sure that they all actually equal K, but the amount of work that would go into showing that is probably not worth actually doing. And so what's it good for? Well, as I said, it's good for extracting information where the Osvaldt-Seidel contact invariant can't give you any. Another thing it's good for, of course, is just detecting tightness. Right? We're not entirely sure, well, we don't know. I don't know that I would even conjecture. I would just say it's a question as to whether or not having spectral order 0 is equivalent to over-twistedness. We don't have any counterexample for that. We would very much hope it's the case. But in any event, it gives, a fairly cheap and easy way of detecting tightness. It's certainly simpler than my theory of consistency. And we can even say it's possibly complete, but we don't know. The idea being that one just has to look at regions near the boundary. If you can show that there are no regions whose J plus is 0, which sort of attached to the contact element, then you can see that the thing can't possibly vanish on the first page of that. And there are sort of simple characterizations one can give in terms of like fractional Dentwist coefficients and things like this that then give you sufficient conditions for tightness. Another thing one can do is refine invariance of Legendrian knots. I'm out of time here, but the idea here is that with these, if you look at, for example, the loss invariance, Glasgow, Osvaldt-Stipschitz, Szabo, you see that these things, they rely on the contact invariant in the complex corresponding to the complement of the knot not vanishing. But we can then say, we can still extract information for cases when it vanishes, so we get a refined invariant there. And really, anywhere you have something which is depending on a contact invariant not vanishing, we can go in and refine it and say a little bit more. So this is still, well, this part of it's not work in progress. These two are. And I think I'm out of time, so I'll stop there.
So was the reason why you had to do this sort of extra bit to get a Z-filter complex because you can't define a grading on the generators such that the so you actually
it's on the differential. Exactly.
Okay, like different terms than differential that have.
I'm a little confused as to what this what is this O is the minimum of the latter guy is the page at which some particular class vanishes in the spectral sequence?
Well, the spectral sequence we associate to this triple. Right, so for each triple we get a different spectral sequence.
Okay, and the content is that you can compute this minimum from any one of those.
Yes, exactly.
Okay.
With the appropriate data. Because
Is
it
it
has to do
possible
with
to say
the choice of,
Is it possible to say what the idea behind why you should be able to do that?
yeah, I actually wanted to go over a quick proof of that. Well, what you want to do is show that, so when you stabilize these things, you want to show that you have an inclusion of complexes in stabilization. So you take your open book decomposition, your arbitrary triple, and then you consider some other triple which realizes the min, and then you take a common stabilization of these things. And the idea being that you then conclude that the common stabilization also realizes this minimum because we have this inclusion of complexes. And so what you want to do is from the triple you started out with, you want to add enough data to, basically what you want to show is that a stabilization is equivalent to adding an extra arc into your gamma. But then you also want to see that if you add enough, there's a bound on the arcs you have to add, which is given by the number of boundary components of your surface, such that once you've added that many, you don't have to add any more. So you start with your surface, and you, based on the number of boundary components it has, you put in enough arcs gamma there that you can realize whatever the minimum is.
But you're using the fact that you have a common stabilization.
Yes.
And this method for detecting tightness, can you say a few more words about that? I mean, is it?
So, well, I mean, suppose there's some chain which is killing the contact generator. And so for this to be, for it to die in the first page of the spectral sequence, it would have to be such that all the guys in the chain have this j plus equals 0, right?
So,
Otherwise, the differential wouldn't see it on the first page.
so hold on a second. Oh, you're just actually referring to your theorem. Sorry, it's a sufficient condition for detecting tightness.
Yes.
So this is just using the fact that if it's over twisted, then this invariant vanishes.
Yes, yes.
Okay, got it. Sorry.
So the idea is that it's not the case that the spectral sequence is invariant,
That's right. We don't.
but nonetheless you can extract when this the filtration, the minimal filtration level by looking at a single
Yes,
thing, even though it's not.
that's right. And it might be true that we can get more invariant information out of the spectral sequence than just this, and we probably can.
But so in particular, I mean, the minimum really varies.
Yes.
But nonetheless, you can see by looking at one thing that it.
No, if you put in, not with a good choice of data. The point is that there's a good choice of data so that you'll get the right minimum. It'll vanish on the correct page.
By data, like, I see. So when you say you can compute it from one open book decomposition, do you start by choosing one good open book decomposition?
No. Arbitrary open book decomposition, but then a good collection of arcs.
I see. Okay.
This vector sequence depends on the choice for the ox.
Yeah. Well, I mean, the ER4 chain complex does as well. Okay, well, we're 5:05, so I'm going to take it on myself. Call it a day.